Hello everybody, welcome to your Lecture 3 Skill Check. Today we're going to be looking at two kinds of calculations. The first is when you conduct a hypothesis test for a population mean when the population standard deviation, sigma, is known. Under this circumstance, we're going to calculate a Z statistic, and so we call this kind of problem a one-sample Z test. We're also going to look at the case where the population standard deviation is unknown. This is something that we learned in our previous class, and this is the case where instead of using a Z statistic, you need to use a T statistic, and so we can call this kind of problem a one-sample T-test. Now, before getting into that, I just want to review again this central limit theorem because it's so important. It's really important you know when this central limit theorem can be applied. The conditions are actually quite simple. First, we need to know that our individual measurements are independent of one another. And how do we assure that's the case? Well, we use an appropriate sampling technique. For example, we could take a simple random sample to get our measurements. So a simple random sample or some other appropriate sampling technique that uses randomization, that's all good. Also, we need to make sure the sample size is no more than 10% of the population size, and that's also to maintain the independence. So if these conditions are true, we'll have measurements that are independent of each other. So that's the first condition. And the second condition, to put it very simply, is the sample size has to be big enough. So if the sample size is large enough, then we can make our approximations as I'm about to talk about. But let's just make sure we know what large enough means. So it all depends on the distribution for individual measurements. If the distribution for those individual measurements is approximately normal, the sample size doesn't need to be very big. 10, 15 or so would be big enough. But if that distribution for individual measurements is very non-normal, let's say it has a very heavy skew to the left or to the right, in that case, you need a larger sample size to appeal in order to ensure that the central limit theorem can be applied. So how big? Typically, we say the sample size needs to be at least 40 when the distribution for those individual measurements is highly non-normal. For example, if it has a big skew to one side. So if the sample size is big enough, then we have two results. The first one is if you take your sample mean and you standardize it, and when you standardize, you're using the standard deviation of that sample mean, then what you're doing is you're calculating a Z statistic. And that Z statistic is approximately normal 0, 1 in distribution. It follows approximately a normal distribution with a mean of 0 and a standard deviation of 1. That's your Z table. And so what do we mean by the standard deviation of the sample mean? Well, that's when you calculate the standard deviation using a population standard deviation, using a known sigma. So that's on one side. And so this approximation holds as long as these conditions for the central limit theorem hold. On the other side, cases where we do not know what the population standard deviation is, we have to use an estimate for that standard deviation. We use the standard deviation of the sample. And so in that case, when you standardize your sample mean, you're using the standard error of y bar instead of the standard deviation. That introduces greater uncertainty into your test statistic. And so the test statistic is no longer Z in approximation. Instead, it's approximately T in distribution, T with n-1 degrees of freedom. So again, I want to emphasize that both of these approximations hold, which means we can calculate confidence intervals or conduct hypothesis tests using our inferential machinery. We can do that provided that these two conditions hold for our sample. Okay, so that's theory in a very little nutshell. Just forget I said that. Okay, so question 1. A company makes batteries for watches. Engineers claim that the mean lifetime Y for one of their products is 4,500 hours with a standard deviation sigma 350 hours. To test this claim, the plant manager takes a random sample of 60 batteries every month. So check it out. What the engineers are saying, what they're providing are population values. They're saying for all of our batteries that we manufacture at this plant, the population mean lifetime for those batteries is 4,500 hours, and the population standard deviation is 350 hours. This is the engineer's claim. And so what the plant manager wants to do is take a sample every month and use the sample mean, conduct a hypothesis test to see if this claim is reasonable. So we're pretending that in December of 2023, the sample mean lifetime for that sample of 60 batteries was 4,320 hours. The question is, does this suggest that the population mean was less than 4,500 hours in December? How do we answer this question? We're going to conduct a hypothesis test at the 5% level of significance to find out, still assuming that the population standard deviation is 350 hours. So, in other words, because we're using a population standard deviation, we're going to conduct a one sample Z test. We're going to calculate a Z statistic. So let's set up the test. So first, we need to recognize that our null hypothesis is that the mean lifetime for batteries, the batteries that were manufactured in the month of December, that mean lifetime is equal to what the engineers claim, 4,500 hours. The alternative that we're testing is that it's less than 4,500 hours. And we're testing at the 5% level of significance. So we can draw a picture of the distribution for our test statistic. It's a standard normal distribution. Looks something like this. Now, all we need to set up the test now is to determine what the critical value is for our test. So what we can do is we can just remember that if you want to make a 90% confidence interval, then the Z score, the critical value for a 90% confidence interval, is plus or minus 1.645. That's the value that puts 5% into each tail of the distribution. And so if we're going to conduct our test at the 5% level of significance, and because it's a lower tail test, we're going to put a critical value here on the left that puts 5% in that lower tail. That critical value is minus 1.645. And so the decision rule is that we will reject the null hypothesis if our test statistic is to the left of this critical value. In other words, if it's less than minus 1.645. Now that the test is set up, we just need to calculate our test statistic. We have our data. The sample mean is 4,320 hours. We have a population standard deviation, and we have a sample size. So our test statistic is a Z statistic because we have sigma. Let's calculate that standard deviation. We just take our standard deviation for an individual measurement. That's a population value, 350 hours, divided by the square root of the sample size. We get about 45 hours as our standard deviation. And so now to calculate our Z statistic, we take our observed mean value for that month of December, 4,320 hours on average. We compare that to the hypothesized value under the null hypothesis, and we scale this distance by the standard deviation. And so what we get in the end is that 4,320 hours is 3.98 standard deviations to the left of the mean value under the null hypothesis. This is a very big distance away from the mean value. So we can guess that we're going to reject the null hypothesis. And indeed, looking back at our decision rule, as long as our test statistic is less than this critical value, we're going to reject. So clearly here, we do reject. So our conclusion, we reject the null hypothesis because the test statistic is less than the critical value for our 5% test. Now, it's often useful to put a number that sort of quantifies the weight of the evidence against the null hypothesis. That number is called a p-value. So here we can approximate the p-value using our Z table. So here's a piece of your Z table. What we want is if we put Z here equal to minus 3.98, we want the area in that lower tail. So we look at our table, we start with minus 3.9, and then we look at 0.08. And so the area in that lower tail would be a number that appears right here. There is no number. Now, why not? The reason there's no number here is because minus 3.98 is so far in the tail that the area in that lower tail is essentially zero. And so, in fact, what the table tells you is that if this z-score is minus 3.9, the area in that lower tail is 0 to 4 decimal places. And so here, we're not at minus 3.9, we're at minus 3.98. We're even further to the left. The area in the tail, which corresponds to the p-value of the test, is 0 to 4 decimal places. And so what's that saying is if the null is true, a test statistic as far to the left as what we observed, or further, is very, very unlikely. And that sort of tells us that probably the null hypothesis isn't true. Because if it was true, this outcome here, our z statistic, would be highly unlikely. So that's the way we're reasoning it out. Here we can say the evidence against the null hypothesis is very strong to overwhelming, right? We have a p-value that's much, much less than this number. So overwhelming evidence against the null hypothesis. Right, so now before I move on, I just want to emphasize now what that means. So think of it practically. The idea was the engineers are saying in our plant where we make batteries, the mean lifetime for our batteries is 4,500 hours. The quality control goes month by month. We take a sample of 60 batteries and we see how long they last. In this particular case, the sample indicated that the mean lifetime of the batteries manufactured during that December of 2023 was statistically significantly less than the claimed value of 4,500. So what does the plant manager now know? The plant manager knows that either the materials that are being used to make those batteries is substandard, or there's something wrong with the manufacturing procedure. So you can see how useful this kind of information would be. We would have to stop our production line and go and try to figure out what's gone wrong. We would test our materials, we would test our manufacturing procedure and try to fix the problem, right? So this is, even though it's a pretend example, I think it conveys sort of in real life how useful these kind of testing procedures can be. Okay, so question 2. A random sample of 40 families in Nova Scotia had a sample mean of 3.2 children per family with a sample standard deviation of 0.97 children per family. Here I'm emphasizing that both of these numbers come from the sample. So we do not know what the population standard deviation is. So what does that tell us? We cannot use a Z statistic. We have to use a T statistic. And so the question here is, could the mean number of children per family for all Nova Scotian families, could that be less than 3.5? Given this data, we're going to conduct a hypothesis test at the 5% level of significance to find out. So, setting up the test, our null hypothesis is that the true mean is 3.5. Our alternative is that the true mean is less than 3.5. We're going to test at the 5% level of significance. I want to just take a moment here to point out, I know both of these examples today are lower tail tests. Of course, it's also possible to do an upper tail test, and we will see examples of that in class and on future videos. I just don't want anyone to go away thinking all hypothesis tests are lower tail tests. It just so happens that it went that way for these examples. So in any case, when you go to draw a picture, and what's this picture going to be? It's the picture of our test statistic. It's going to be a t-distribution. And it's going to be a t-distribution approximately 39 degrees of freedom. 39 because the sample size is 40. Why do we say approximately? Because we're appealing to the central limit theorem, which tells us that our t-statistic will be approximately, or our test statistic, I will say, will be approximately t in distribution. We don't know for sure if it's going to be exactly t because we don't know what the distribution for individual measurements is. But what we can say is the sample size of 40 is big enough that this approximation is going to be a good one. So we have our approximation. We need to find a critical value, just like before, in order to set up our decision rule. So we're going to find a value here in the lower tail of the distribution, and we can say that if our test statistic is to the left of that value, then we're going to reject our null. How do we find that value? We look at the t-table. So here is a part of a t-table. The degrees of freedom we need is 39. 39 doesn't appear on our table, so we have to use a degrees of freedom that is as close as possible to 39 without going over. That's 35 degrees of freedom. So we got that. Now we want a critical value that puts 5% into that lower tail. That critical value is going to be in this column. See, the one-tail probability of 5%. And so our critical value, 1.690, puts 5% in the upper tail. And so minus 1.690 puts 5% in the lower tail. So that's our critical value for our test. So we can just set that in. And now we have our decision rule. What's next? We just need to now calculate our test statistic, our t statistic, and compare it to this critical value. So we have our data. We have a sample mean. We have a sample standard deviation and a sample size. We're going to calculate a t statistic. We're going to be dividing by a standard error of that sample mean. So let's calculate that first. The standard error of the sample mean is the standard deviation of the sample divided by the square root of the sample size, 0.97 over root 40. It's this number, 0.1435. And so now we can get our test statistic. We're looking at the distance between the mean value of our sample and the mean value under the null hypothesis. That distance in terms of standard deviations is minus 1.96. So what this number tells us is that our test statistic is 1.96 standard deviations less, sorry, let me take it back. Our sample mean is 1.96 standard deviations less than the mean under the null hypothesis. Now, I just noticed that I have a little mistake on this slide. You may or may not have noticed it. That shouldn't be a Z, that should be a T. So I'm just going to fix that. Hopefully this will still record as I do so. Whoops, not like that, like this. Yeah, so you can see how easy it is to make a mistake. And that just means we have to continuously double check our work. I myself am very prone to making careless errors like this one. And so I typically will double check or triple check my work as I go. Anyway, that's neither here nor there. Now that we have our test statistic, we can compare it to our decision rule and to draw our conclusion. So, clearly, we're going to reject our null hypothesis because the test statistic minus 1.96 is less than the critical value for our 5% test. Okay, now the last step is we would like to get a number that quantifies the weight of the evidence against the null hypothesis. In other words, we want to get a p-value for the test. And so to do that, we need to go again to our t-table. Now, again, we're working with 35 degrees of freedom because that's the best we can do with our table. And now the idea then is for a lower tail test, if we put right here our test statistic, minus 1.96, the area in that lower tail is the p-value of the test. Now, the table doesn't give us negative values, it gives us positive values. So instead of going minus 1.96, if we could put a plus 1.96 and get the area in the upper tail, that would be the same area as in the lower tail if we were at minus 1.96, right? Because of symmetry. So when we estimate our p-value using the t-table, we're always going to just use a positive value for that test statistic, whether it's positive or not. So here's the point. If our test statistic was 1.69 right here, then the area in the upper tail would be 5%. And that would be our p-value. If our test statistic was 2.03, then the area in that upper tail would be 2.5%. And that would be our p-value. But our test statistic actually is in between these two numbers. It's more than 1.69, but it's a little bit less than 2.03. So we can say then that the area in the upper tail, when this t statistic is 1.96, that area is between 2.5% and 5%. And so that's the best we can do to estimate what the p-value is using our table. We can say the p-value is going to be less than 5% for sure, but it's also more than 2.5%. That's how we get from the table. Okay, so the approximate p-value for the test is therefore something less than 5%. And just to review again the meaning of the p-value, assuming the null is true, the probability of getting a test statistic of minus 1.96 or further to the left is less than 5%. That's what it means to be a p-value. So in other words, this result is unlikely if the null is true. How unlikely? It's less than 5%. So it's quite unlikely. And so that's why we reject the null hypothesis at the 5% level of significance. Now let's just look at our adjectives for the strength of the evidence. Here, the evidence against the null hypothesis is only moderate because we're in this interval here. We're less than 5%. We're bigger than 2.5%, which means we're also bigger than 1%. So this is where a p-value lies, moderate evidence only against the null hypothesis. Okay, so that's it for this skill check. I really hope you found that useful. Just if you have any questions about this, just put a comment below the video. I'll be looking at those comments if there are any, and I will answer those questions either in comment or I'll answer that question in class. So that's all for today. I'll say bye for now, and I'll see you in class. Bye-bye.